Okay, so reminders. This is the second to last week. Next week is dead week. Remember that you've got two major things to turn in this week. The design document is due on Thursday, hard copy, that is printed out with a rubric on top, and that is your final draft. So that's the one that is going to count towards your final grade. And then, of course, you've got your assignment 7 due this Friday at midnight, as usual. That is your sorted list abstract data type, where you have to implement a sorted list somehow. And then reminder next week, you've got your final assignment 8 due. That's all written, and that will be due hard copy, either handwritten, or if you really want to use a typesetting system, go ahead and use it. That's due on Thursday of next week. So keep those due dates in mind. And of course, if you are doing the bonus assignment, if you're doing option A, where you are resubmitting or want to be reevaluated for up to 50% of your points back on any one assignment, you have to be doing that in the next couple of weeks with the LA that graded it. And then, of course, the bigger bonus, the 100-point bonus, that would be due on Friday of dead week. And if you are going to attempt that, I would suggest that you get started now because it is not at all trivial. Right? And it involves binary search trees. So as a review of what we were looking at last week, a binary search tree is a tree, it's a binary tree that stores keys, unique keys. You can have duplication if you really want to. You just have to handle it one way or another. We're going to go ahead and look at unique keys here, such that if you look at any key here, everything in the left subtree is less than that key, and everything in the right subtree here is greater than that key. And I've left a gap here because as a review, I want to ask you, what could I put here? Could I put, I don't know, could I put 40 over here? No, that would be a violation, right? That's less than 130, but it's greater than 80, and also it's less than 70. It should be on this side of the tree. So could I put in 170 here? Well, 170 is less than 80, right? But it's not, it's greater than 80, but it's not less than 130. So no, I can't put 170 here. What's the range of values that I could put here? It has to be greater than 80, right? And what else? It has to be less than 130. So I could put in 81, 82, ... all the way up to 129. So I'll go ahead and put in, say, 90. Right? That's perfectly fine. So keep that in mind. And it's inductive. Everything in the left subtree of 30 has to be less than 30. Everything in the right subtree of 30 has to be greater than 30. But it has to inductively satisfy all those properties for every single node, going all the way down the tree. So we briefly looked at or outlined how to do searching. Say that we want to search for, 15. Right? A successful search because it's down here. What do? We come in and we start at the root. And we see that 15 is less than 70, so because of the binary search tree property, we have to traverse left. Right? And then we look at 30 and see that 15 is still less than 30, so we'll go ahead and traverse left again. All right? I screwed up, didn't I? 25. There we go. All right. We see that 15, we'll still search for 15 here. We'll go ahead and search for 15. It's less than 20, so we go over here. Right? And now this is no longer a successful search, by the way. But if it were a successful search, then it would be the right child of 10. Right? And at this point, the current node that we're looking at, that we've traversed down here, does not exist. So phi, null, whatever placeholder you want to use there. And we end our search with does not exist. All right? Let's go do that again, but let's do it with one that we know that will be successful, say 90. So I come in on 70. Right? It's greater than, the thing I'm searching for is greater than that. So I go down to 130. 90 is less than 130, so I come over here. Right? And I come over here. And I find what I'm looking for. Right? And then whatever data is stored in that node, I extract that and process it and do whatever I'm going to do with it. Right? So both of these searches were proportional to the depth, right? In one case, I had to go all the way down to the bottom of the tree for an unsuccessful search. Sometimes you'll get lucky, right? What if I were searching for 70? Right? Then I would come in here and I would immediately stop with one comparison. Right? There's going to be one comparison here. When I did 90, I did one comparison, 2, 3, 4 comparisons. And when I did a search for 15 here, I did 1, 2, 3, 4 comparisons to get out of the tree. Right? So at most, by doing this, at most, D comparisons are made to search for any node where D is the depth of the tree. Therefore, this searching is order D. But as we've already seen, a tree can be skewed. It can be a degenerative tree where basically you just have a linked list. And then the depth is proportional to order n. Ideally, we would like our depth to be order log n so that we can kind of get the behavior of binary search. Let's go ahead and codify this now. We outlined this last time. Let's go ahead and codify this with some pseudocode. Okay? So for that, I'm going to label my input. My input is simply going to be a binary search tree, BST, T. Right? Binary search tree, it's okay to abbreviate those or take an acronym here. Right? Our output will be, let's say the node, the node containing a key k. So that should have been part of my input too, right? A key value k, right? Or in the event that we are not successful, searching for 15, say, in the event that we're not successful, we'll go ahead and output phi if no such element. Okay? So I want to outline this here. Where do I start? Well, remember, I'm going down the tree here, so I'm probably going to want to keep track of the current node. And that current node is going to be initialized to the tree's root. Right? So what I'm going to do is I'm going to create a node here, call it current, right? And I'll start at t's root. Right? And I'll go ahead and even put in a comment here that cur is the current node. Right? If I were doing this in Java, I would go ahead and use current node, right? And I would use a more expressive variable name. Okay. Now what do I want to do? When did I stop? Right? I stopped when the current node is no longer valid, right? That's one stopping condition. Another stopping condition is when you found what you're looking for. Let's go ahead and take care of this one first. I'm going to continue going left or right, or stopping and saying, "Oh, I found what I found what I'm looking for," until I get down to an unsuccessful search. Right? So while the current node is not equal to phi, or whatever placeholder value you want. If it's null, if you're in Java, then it'd be null, or if it's some sentinel value or some special flag value that you're using to get through this entire loop here. Right? So while it's not null, I'm going to compare the key in the current node to the key that I'm searching for. Right? So that's the first condition. Right? My other stopping condition here is if the current node current node's key value is equal to the thing that I'm searching for here, then I've found my needle in the haystack. So what should I do? I should stop and output it. Right? Output, and I think that we said that we're going to output the node, so I'll go ahead and output current, or cur. Right? Otherwise, if it's not equal, I'm searching for 15 here, I need to either go left or right. So the relative ordering of this key is going to tell me whether I need to go left or I need to go right. And that's just another check. Else if the current node's key is, say, less than k, then where do I need to go? The current node's key is less than what I'm searching for. So do I need to go left or right? The thing that I'm searching for is bigger than this key. That's another way of saying it. So I need to go right. Right? So I will update current to be current's left child, or sorry, right child. There we go. Go right. Right? Now there's only one other condition here, but I will explicitly say what it is with an else if condition. Right? This is not necessary in real code. But if the current key is greater than the thing that I'm searching for, then I need to go left. So I'll update current to current's left child. Right? There. Those are the only three conditions. At some point, you will either find what you're looking for, in which case you'll stop and output the current node, or you'll fall off the edge of the tree, in which case you'll break out of this loop. If you've broken out of this loop, what does that tell you? It's an unsuccessful search. So I will output what? Fee, or null, or whatever other placeholder you want. Okay? So there's the full pseudocode for traversing a binary search tree and actually searching for something. Okay? All right. Well, what's another operation that we want to do? We have to get stuff in our tree to begin with, right? It doesn't just magically appear. So I want to be able to insert stuff into a binary search tree. Let's go ahead and take this example here. And what if I wanted to insert, I don't know if I have another color here. Yeah, I do, blue. Right? So insert. Let's say, I don't know, let's insert 75. Okay? Where could I insert it here? Right? Well, what if I started at the top and pushed 70 out? Right? I'll put 75 right here. Right? Then where would the 70 go? If 75 were here right now, it'd have to go to the left, right? 70 would have to go to the left because it's less than 75. And so now I just have another problem of, well, now I need to push out 30 or something like that. I don't want to have to disrupt the entire structure of this tree just to insert one new node. So I'm going to take a different approach. I'm going to disturb the structure, we sometimes call that topology, the topology of this tree as little as possible. And by doing that, the way that I'm going to do that is simply by budding a new leaf node. Right? So if I'm going to go ahead and insert this as a leaf node, then I need to find out where would it belong. Right? The idea is I'm going to search for it. So I come in here, 70 is less than 75, so I go right. Let me go ahead and draw this. 75 is less than 130, so I come down here to 80. 75 is less than 80, so I come down here and I see, oh, there's nothing there. I have room to put a new leaf in there. Right? And so it's going to become the left child of 80. Okay? So that's the basic approach. To insert, insertion, you are going to always insert as a new leaf, right? Well, that involves, as a first step, step one, you need to find where it is, right? Find, via search, where the key would be if it existed. And by the way, you can also go ahead and take a design decision here. Well, what if 80 is already in there and I want to insert 80 again? Do we allow duplicates? No. So I'm going to go ahead and reject that. I can throw an exception. You try to insert a duplicate. We're not going to allow that. I could say that it's no operation. Oh, it exists. I'm not going to do anything about that. I could return a flag value to say false. It had no effect. Right? True. It had an effect. I could do all the same things that we did with our other collection data structures that we've looked at so far. So I will assume that it doesn't exist, because if it doesn't exist, then that's a separate issue. You can go ahead and handle that, and that's a design decision that's left up to you. We're going to search for where it would have existed if it had been there. Right? And then we insert as a new left or right child. Right? In other words, I'm going to have to update the left child of 80 here. I'm going to have to create a new node, put my key into it, and I'm going to have to make it the new left child of 80. And if I'm keeping track of the parent, I need to make sure that I update the parent to this node. So what does that tell you about searching? If I come in here, 70, 130, 80, and I'm right here, if I only keep track of the current node, then that's going to be phi, null, whatever you want. What I actually need is the parent where I'm inserting it. So I can't just use this as a subroutine. I'm going to actually have to keep track of the current node, which eventually is ultimately phi, but I'm also going to have to keep track of the previous node. So the way that is going to work, my two fingers here are now two variables. I'm going to come in, my current node is going to start where it was before, at the root. My previous node is going to start at phi, whatever you want, right? And as I start traversing this list, this tree, I'm going to want to update both the current and the previous so that when I get down here to this one, I still have access to this previous node, and I can make it a new child, and I can make the new child point back to it as its parent. So it's going to be very, very similar to this, except that I'm going to want to keep track of two other things. So rather than rewriting all of the pseudocode, I'm going to go ahead and come back in here and insert a few things in pencil. Right? So I need to start my previous. This is why I called it current, because now I'll have previous. And I'll initialize that to phi, null, because again, there is no previous. If you start at the root, you weren't anywhere before, so there is no previous. While the current is still going on like this, eventually you're going to break out of it because you're assuming that it doesn't exist. So this is really not that big of a deal, except for instead of outputting it, you could then choose to throw your exception or return a flag value or something like that. Otherwise, if you go down, then you need to update the current to the right child. You need to update the current to the left child. Before I update those things, I need to update the previous. The previous is going to be updated to the current. Right? Could I have done that after? Could I have done it here? Previous is updated to current? No, because then that's out of order, right? I don't want the new left child. I want the actual parent before it. So I will go ahead and put it in the correct order here. Current. Right? Update the previous, then update the current. Right? And at this point, after you're done here, then insert. Right? So this we will write separately here. All right? So given a previous node and a current node, which is actually quite useless because it's equal to phi, right? So we can go ahead and ignore that already. Given a previous node, what we want to do is we want to insert a key, k, as its proper child. All right? This is my parent, basically. Here's my previous. This is the previous. And I need to either insert it as a left child or I need to insert it as a right child. So we need to determine that first. So what I'm going to do first is I'm going to create the new child node. Right? I'm going to go ahead and create a new node. I'll go ahead and call it U. Right? This is a new node with key k. Right? And so I've created this new node. It's either over here or over here. I don't know yet. But there's this new node, k. Right? And what I need to first do is I need to make sure that k is pointing back to its parent. So u.parent is equal to, or go ahead and use left arrow here, is going to be the previous. Right? So that has given that relation back up. Now I need to determine, should this new node right here be a left child or a right child? And that's just another simple check. If the previous.key, right, is, say, less than k, right? So the previous key is less than this key over here. So where does this one need to be? On the right, right? So I will update previous as right, previous.rightChild, to be my new node u. Right? And then I will be explicit about this. Come back up over here. Else if, right? There's no other. I mean, it could be equal, but you would have taken care of that already. Else if the previous dot key is greater than k, then it needs to become its right child. Left child. Left child becomes U. There. And that's it. So what's the complexity of this? Right? Well, we had to go through this process over here. And we've already said that this process is order D. Right? Once we've done that process, then it's just a simple create a new node, right? Update a pointer variable or a reference variable, update another reference variable based on one of two comparisons here. So all of this here is going to be, this part is going to be order 1. Right? It's just constant. It doesn't depend on how many nodes are in the tree because you already got there. You already got to the previous. However, to find it, right, step 1 up here, this is going to be order D. Right? So in total, if you want to look at it this way, then it's order D plus order 1, which is simply just order D. Right? Assuming that the D is the depth of the tree. Okay. Well, that takes us to the last one. We've done searching. We've done insertion. What about deletion? Let me go ahead and create another binary search tree here. I'll go ahead and make it full. So 10, 30, 20, and let's go with 40 over here, right? And then 50, 60, and oh, darn it, I should have gone 70 there and then 60 there. That's what I wanted to do. Okay, so there's a binary search tree. I didn't screw it up this time. Suppose that we wanted to delete 40. Right? Actually, no. Let's start out with an easier one first. Let's suppose that we wanted to delete 30. Right? Well, what's the first thing that we need to do? Find it, right? So step 1, find it. Right? And we already know how to do that. How do we do that? Same thing as over here, right? It's searching, right? You search for it. Once you've found it, here it is. What can you do with it? It's a leaf, right? So when you're trimming the tree and you just want to cut off one leaf, is it going to be too damaging to the tree? No. So if it's a leaf, then just simply delete it. And what do we mean by deleting it? How would I end up deleting this, say, in pseudocode? So I would look up at its parent, and I would set its child reference to null or phi or whatever you're going to do, right? That's essentially cutting this off. I don't need to, in Java, if this were another programming language like C or C++, you'd have to update maybe the parent pointer, and then you'd have to clean this up and call free or something like that, or a destructor or something, right? But if it's Java, as long as you sever this connection, then it takes care of, garbage collection takes care of it for you. Right? What if I wanted to delete, say, instead 20, delete 20? Right. Well, again, first step is find it. Right. And there it is. Right. But what's the problem here? It has children. Right. Let me go ahead and put in one more here, 5, to make this non-full. And let's consider deleting 10 instead. Right. Okay. So suppose it has a bunch of other stuff hanging off of it, 4, 3, 2, whatever. Right? I want to delete 10. Well, if I cover up the rest of this tree, what does that look like to you? It's just a linked list, right? Well, how do you delete a node from a linked list? You cut it out, and then you make it so that 20 is referring to 5, and that 5 is then referring back to 20. Right? Does that change? Does that disrupt the binary search tree property? No. Does it It makes everything over here, slightly more shallow now in the tree. It's not as deep, but that's fine. Overall, the structure of the tree is preserved. Right? Now, you can't do this with a real tree. You can't take a branch and then just cut a little piece out of it and then put those branches back together, unless you're, there is a term for that. I forgot what it's called, but when you take one tree and clipping from one tree and put it onto another tree, it's grafting, I think it's called. So you can graft trees in real life. Some trees you can at least. And you can graft your trees right here. So if I'm going to delete 10, find it. If it has one child, then what can I do with it? I can promote its single child up. Right? And that's what I've done here, basically what I'm doing by circumventing 10 here. 5 becomes the new left child of 20. And you're good to go. That's it. But now, going back to what we were looking at before, what if it has both children? Delete. And I'll go all the way up to the top here. What if we wanted to delete 40 here? Let's try doing the same trick. Okay, well, it has 20 and 60 as children, so let's go ahead and promote 60 up here. All right, I'll go ahead and cross this out. 60 is now promoted, and now I've got a gap here. I've got a gap that I need to fill. 50, 70, okay. Go ahead and promote one of those children up. Which one do you want to promote up? 50? All right, let's go ahead and put up 50. And of course, 50 is a leaf, so there's no problem in deleting that node. Is that a binary search tree? 60. Everything over here in the right subtree needs to be greater. Is 50 greater than 60? Nope, so this didn't work. Well, maybe I just screwed up here, and well, maybe it should have been 70 instead, right? I'll leave 50 here, and I should have promoted 70 up instead, and then I can cut it off. Is that a binary search tree? Same exact problem. 50 is not greater than 60, right? So this is kind of symmetric. So if you run through the same example here with promoting up 20, you'll have a problem with either 10 or 30, or you'll have a problem with 30 being on the wrong side of the tree, right? So none of these are going to work. There we go. All right. So let's rethink this. I do want to delete 40. So suppose that I take it out, right? And now, unfortunately, I don't have white out here, but it is it's empty now. Right? What could I put there? And let's go ahead and forget this for now. Right? What could I put there so that the binary search tree is satisfied? We already said that you can't put 20 up there. You already said that you can't put 60 up there. But there's some other candidates here that you could put up there. Can you put 10 up there? No, because 20 and 30 are not less than 10. Can you put 70 up there? No, because then 60 and 50 would be on the wrong side. So what could you put up there? I could put 30 there, right? And if I deleted 30, is that a binary search tree? Yeah. What if I went the other direction, and what if I put 50 up there instead? Deleting 50. Is that a binary search tree? Yeah. So what is it about 30 and 50 that make them good candidates? Look at this left subtree. Everything in the left subtree is less than what was here at the node. What can you say about 30 among all these elements here? It's the greatest value, right? It's the maximum value. Now, likewise, over here in the right subtree, everything is greater than the key that was up here. What can you say about 50 among these three elements? It's the smallest value. It's the minimum value, right? So if it has two children, so delete 40. If it has two children, then you have a choice to make, right? You can either go, and I'll go over here, go to the left subtree and find, what did I want to find? I wanted to find the maximum, the max, and promote it up. it to the empty node. Right? Well, what's my other option? Go to the right subtree and find the minimum and promote it up to the empty node. Now, immediately here I see, well, what if there's a problem here, right? What if it has 2 children, right? So what if I go ahead and find the minimum, right? And this was in the right subtree. So here's the right subtree, and then let's go up even further. And I went down and I found the minimum. Uh-oh, what if it has 2 children, A and B, right? Then it wasn't the minimum. Why? What's the binary search tree property? Everything over here is less than this. Everything over here is greater than this. So therefore, was this the minimum? No, because A is less, right? So you can have a situation where you've got the minimum. There will never be a left child for the minimum value in a tree. Right? Otherwise, go to that left child and you found something smaller. If it has a left child, keep going to that, then this is the algorithm that we'll develop. Keep going to the left child until you have no left child. That's your minimum value. Right? You can, however, have something that is greater than it. Right? And so now we've got a situation where I want to promote this minimum value up to the root of the tree, but it has a right child. All right, how do I handle that? If it has 1 child, all you have to do is promote its single child up. We've already taken care of that situation. Right? So this is the idea. All you need to do is figure out which case you've got. Find it first. If it's a leaf, then simply delete it. If it has 1 child, promote its single child up. Otherwise, you'll need to go to the right subtree or the left subtree. It doesn't matter which one you choose. You can always go to the right. You can always go to the left. You can randomly select between the two, or go first left and then set a flag variable to remember that you need to go right for the other one. But you need to find this stuff, right? And then once you've done that, you have either a case where it's a leaf, or you have a case where it only has 1 child, and you know how to deal with those, right? So what I want to do, instead of writing all that out, I'll leave that as an exercise. I do want to write out how to find the minimum or find the maximum. And it's going to be the same exact algorithm, so I'll go ahead and go with finding the minimum. So our input here is going to be a tree node, U, right? And our output will be the node containing the minimum value minimum value key in the tree rooted at U. Right? So you could think of this as starting at the root of the entire tree, or you could think of this as going to an internal node somewhere in the tree and then finding the minimum value there. Right? Well, there's one corner case immediately. Right? I want to find the minimum value. So what if I were given a node that looks like this? Right? Here's U. All right, and then there might be a right subtree or not. Right? But there's no left child. What can you say immediately? U is the minimum. Right? We'll go ahead and subsume that with a while loop here. I'm going to go ahead and start out with a current node. Current node, I'll go ahead and start at U. Right? Then I'm going to have a while loop very similar to what we looked at before, while the current node is not equal to phi. Right? Actually, will it ever be equal to phi? Assuming that the input was not invalid, am I ever going to want to go past the tree? So I'm going to want to go into the tree, then find the minimum. Do I want to go one more step and lose my current node here? Probably not. So unfortunately, I did it in Sharpie here already. Let's rethink where do we want to stop? I don't want to stop here beyond the tree. I want to stop where? Right here at that last node. So what condition will tell me that I need to stop? I need to look at the left child And while the left child of the current node is not null, then go to it. Right? So let me go ahead and fix this. While use left child is not null, then that means that you can keep going to its left child. You can go to the left child, you can go to the left child, you can go to the left child. So I'm going to simply update current. Oops, sorry. Yeah, you're right. It should be cur. There we go. Current is going to be current's left child. There we go. That's all you're going to do in the loop. You're just going to keep going down to the left, 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 left until you can go no further. It doesn't matter if it has a right child or not. That's going to be the minimum value of the tree of the node rooted at U. Right? And so then we'll output cur. It's as simple as that. Right? Again, the idea here. Let me go ahead and go with this larger tree that I wrote. If I start here, and let's say that whatever was there before 40 was restored, I simply need to go left, 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 left until I find the minimum value. Right? What would it look like for finding the maximum value? Right child, right child. Go right, 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 until you can go no further. This one will take care of the case that I mentioned before, where we're given U and it's already the minimum. Well, this while loop will never execute, and so you're going to end up outputting U, which is the minimum. Right? So 3 lines of code, pseudocode, and that's it. Right? That's all it takes to find the minimum. Now let's reason. What is the complexity of this? Right? At most, how many iterations are you going to have to go? Right? Like a linked list, updating to the next node, next node, next node. That's our elementary operation. At most, how many times would we have to end up doing this? Order D, the depth of the tree. Right? And so we've got another operation that is order D. Again, if you look back to our cases here, you need to find it. In other words, you need to search for it. You could be very high up in the tree, in which case you might still need to find you could go halfway into the tree, which is still order D, to find it, but then the rest of the halfway to find the minimum value to replace it. In either case, you're going to do things proportional to the depth here. Okay. So finding the minimum, easy. Once you find it, we've already done that as well. This is a simple detection. If it has no children, if the left child is null and the right child is null, then it's a leaf. All you need to do is delete it. If it has one child, that is, the left child is null, but the right child is not null, or the right child is null and the left child is not null, then you've got this case. Else, then you need to go down to the left child or the right child and find the minimum or the maximum among those two things. Okay? And we've already got a subroutine to do that for us. I would put this into another function because that seems pretty useful already. Right? One last thing I want to call to your attention with respect to trees before we do a summary here and then move on from binary search trees is let me go ahead and take that tree again. What was it? 10, 20, 30, 40. And I'll stop drawing all the circles. 50, 60, 70. There we go. As a quick review here, let's do a pre-order traversal, an in-order traversal, and a post-order traversal on this. So let's go ahead and go with a pre-order traversal. Pre-order traversal. Right? That is, we're going to enumerate the root, then the left, then the right. So what's the very first thing that we output here? 40. Then we go down to its left subtree, and we need to do a pre-order traversal on this subtree here. So it'll be 20. And then we go to the left, 10. And then go to the right, 30. And at this point, we did the root, we did the left subtree. Now we need to do the right subtree. So what's the next thing that gets enumerated? 60. Then 50. Then 70. Okay? That's a pre-order traversal. Let me go ahead and do a post-order traversal first, or next. What's the difference? With a pre-order traversal, we go root, left, right. With a post-order traversal, we do left, right, and then root. So what's the very last thing that I'm going to output with my post-order traversal here? 40. Right? Let's go ahead and do it in full, though. I want to do the left subtree first. I want to do the left subtree first. I want to do the left subtree first, but it's empty, so I don't do anything. I want to do the right subtree next, but it's empty, so I don't do anything. So the post-order traversal here gives you 10. Right? Then before I do 20, I need to do its right subtree. So 30, then 20. Right? And at this point, I've done the entire left subtree, but before I do 40, I need to do the right subtree next. So before I do the root, I need to do left, then right, then root. So it'll be 50, 70, and 60. Then after I'm all done, then we've got 40. Again, this is not the reversal of a pre-order traversal. They each give you different things. But now what I want to do is, let's look at an in-order traversal, where I'm doing left, root, right. So if I do the left subtree first, then I do the left subtree first, what's the first thing I get? 10. Now before I do the right subtree, again, I'm doing the root next, so it'll be 20. Then 30. I've done the entire left subtree here, so let's do the root of the entire tree, and then go on to the right subtree. I do the left, root, then right. 50, 60, 70. Tell me what you observe about that in-order traversal right there. It's in order. That's why we call it an in-order traversal. Because if you do an in-order traversal on a binary search tree, you will get exactly the order, the elements in order, right? And so that's why we call it an in-order traversal. Now, if you've got just a generic tree, then without that binary search tree structure, you could get anything that you want because there's no ordering on it. Okay? So as a quick summary here, binary search trees offer order D operations, search, insert, and delete operations. However, the depth may be degenerate. In other words, D could be order n, right? Just like in a linked list, right? Ideally, with a balanced binary search tree, this goes back all the way to the last week, Tuesday, where we did the analysis of why do we want trees, because if you look at them as balanced trees and they're full, with a balanced binary search tree, D is going to be order log n. Right? So you basically get the performance of binary search, not only for searching, but also for insertions and deletions, if you can guarantee this. And you don't have to have random access, like an array list. Right? And you can insert things efficiently. Even with an array list, if you sort an array list and you still need to insert something in the center, yeah, you can find where it needs to be efficiently using binary search, but that still means that you have to move stuff out so that you have a gap there to put something in. You don't have any of those problems with a binary search tree. Right? It solves all of those problems. Right? It still has some problems here because we have no guarantee on this. Right? However, there do exist many variations that guarantee the depth is going to be logarithmic. Right? For example, AVL trees, 2-3 or B trees, which are used extensively in database implementations. What else? There's splay trees, there's red-black trees. Right? If you do a Wikipedia search for balanced binary search trees, you will come up with a dozen different variations, each one of them achieving this guarantee in a different way. A lot of them end up rebalancing stuff. So just as a preview here, we usually cover AVL trees and say CS3, but here's the idea. Say that you've got a skewed tree. So I don't know, 10, 20, and 30. Right? That depth is not ideal. Ideally, you would like a depth 1 tree here. So I've drawn it as a hill here. So what you can do is you can go ahead and hook onto the node here. It's unbalanced this direction. So what you can do is you can drag it over the hill. And when you drag these things up over the hill, 20 becomes the new root. 10 is now on the other side of the hill, and 30 is still on that other side of the hill, but it's been raised up a little bit. So instead of a depth 1, 2 tree, now you've got a depth 1 tree, and it's balanced. Right? And that's the basic idea of, say, AVL trees. 2, 3 trees work by allowing more than one key in a node and keeping everything shallow. And then if you insert something in a new node and a node gets too full, basically you break it apart and then promote it up, and you could end up increasing the depth by 1. When it's too full, then you can increase the depth by 1. Right? But those are all details that are say in Computer Science 3, or that I'd let you look up yourself. Red-black trees are of particular interest. I won't talk about how they work, but they basically have the same kind of rotations as AVL trees. But I will mention that if you are going to use Java, Java has a red-black tree implementation that guarantees that the depth will always be logarithmic. Does anybody know what it is? It's a tree set, right? And it is parameterized like this. As the name suggests, it's a set. Why would you not want this to be a list? Why would you want a tree list? What does that imply in Java? It does imply that it has a linear order. Well, we kind of have a linear order, right? If I do an in-order traversal, I can get everything sorted. But what else? What's the difference between a list and a set? A list, an array list. What can I do with it? I can arbitrarily insert stuff. If you've got 5 elements here, I'll go ahead and insert something right there. Right? Does that mean necessarily that it's in order? Say 1, 2, 3, 4, 5, and I've got 42. I'll go ahead and insert it right there. I'm able to do that with an array list. Should I be able to do that with a sorted list? Probably not. So you don't want a list. What you want is a set. A set means that you can't arbitrarily insert something. I think it is like an add method, .add element, right? And this inserts the element where it needs to be, right? Can you get an arbitrary element? Also no, because it's a set. But it is, it's iterable, right? It's iterable. I shouldn't have done that. That's not a function that you call it. It's a iterator, I think it is. It's iterable, meaning that you can put it into a fancy enhanced for loop. You can use an enhanced for loop to iterate over the elements. How do you think it works if it's a tree implementation? What kind of ordering do you think it gives you if you just iterate over them? What would you want if you have a binary search tree? Which one would you want? Why are you using an ordered tree to begin with? So that you can get a sorted list, basically, right? It performs an in-order traversal so that you can put stuff in and it takes care of it for you. You can take stuff out and it's all sorted for you, right? It comes out in the sorted order that that's there, right? It's kind of like what you're doing in your homework right now. And if you want to, you can use a binary search. You can implement a binary search tree if you really want to for assignment 7. I would suggest that that you get that you can. The vast majority of people are going to probably do it a linked list implementation or an array-based list implementation, and that's perfectly fine. If you want to go, and challenge yourself and implement a tree set yourself, you can't use tree set inside or outside of your classes, but you can use tree set to see what a good design would look like. You can't arbitrarily add elements. You could just add elements. Maybe you could implement the iterable interface here and use it in an in-order traversal because you get stuff out in a sorted order. What else was it about that? Oh, and then finally, how does it do its ordering? Right? It's not always integers. It's not always strings. So those are several people have asked, can we go ahead and implement the comparable interface? Yeah, you can, but you only get one ordering out of that. Instead, how do you think that this tree set works? How does it order something? Given this thing T and this thing T, do I need to go left or do I need to go right or, according to the relative ordering of those things? Right? You use a comparator. Uses a comparator at instantiation to determine ordering. It does fall back to the comparable interface so that you don't have to create a comparator for, like, say, integers or strings or something like that. But this is the normal way of doing it. Right? You give it a comparator when you create it for elements of type T that you parameterize on, and then it takes care of everything for you. You can put stuff in. You can iterate over that stuff. You can delete stuff if you really want to. I think there is a .remove method, and then T element, right? And it'll find it for you, it'll remove it for you, and then it'll fix the tree for you. And because it's a red-black tree implementation, it'll rebalance the tree to guarantee that there's an order log n guarantee, depth guarantee. Right. So in practice, don't write your own. Right? For assignment 7, do write your own. Again, you don't have to go with a binary search tree. If you want to challenge yourself, great. If you've already got it done and you did it in a linked list or an array-based list, that's kind of what we were expecting. Do understand, though, that a linked list or an array-based list for large data, it's going to be linear on all of its methods. This, however, will always be order log n. Right? Okay. So again, we're not going to get to the point where we've got guarantees on order log n for binary search trees. But I am going to show you a variation on a data structure, a tree data structure, where you do have such a guarantee. Right? And it's called you've heard the word before, it's called a heap. Right? Heaps. Okay? So just in plain old English, what is a heap? It's a pile, right? It's a pile of stuff, right? Pile of garbage or whatever, right? Now, if you throw something onto the heap, right? If you just throw something onto the top of the heap, do you expect it to stay there? No, it'll trickle down until maybe it ends up over here, or maybe it goes over here and it ends up there. Maybe if it's heavy or if it just fit just right, maybe it does go up there. Maybe you throw it down here, lower into the heap, and it stays there, right? But this heap, does it denote or connote any sort of organization, right? Well, I don't know. If you've got a pile of clothes at home and there's a dirty pile and there's a clean pile, right? And you throw them onto the heap, that's organized in the sense that they're all dirty and those are all clean still, right? And then you go and you do laundry, so you take that heap and you put it in the laundry, you clean it, and then you throw those things onto the clean pile, right? So a heap is a pile. There is some organization, right? But there's also no control by you on where stuff goes, right? And that's basically the idea of this actual data structure. It's not going to be fully organized. So we're not going to have the full organization of a binary search tree where we can find anything proportional to the depth. There is going to be some organization, meaning that we've kind of got a situation as before with stacks and queues. We have a linked list and an array-based list, but to make them efficient, we're going to basically restrict access. You're going to only be restricted to 2 basic operations rather than an arbitrary insert, arbitrary delete, arbitrary retrieval. You're going to be limited to 2 operations. And this is for a min heap. You can get the minimum element, right? And you can add an element to the heap. Again, you have no control on where it ends up. So you can't arbitrarily insert it. Oh, I want to stick it right there, right? You've got this heap. Kind of like a stack, right? If it's somewhat organized or disorganized, if you try to put something in the middle of the heap, you might then cause an avalanche or something like that. So we're going to add something to the heap. The heap decides where it goes, right? If you throw it on the top, then it ends up somewhere. You can get the minimum element. That's the sum organization that I'm talking about here. Okay? So, before we go on, though, where else have you seen the term heap in computer science so far? Memory allocation. We've got 2 types of memory allocation, the stack and the heap. A stack is very small and organized, right? A stack frame goes on top, goes on top, goes on top, goes on top. You pop them off, pop them off, pop them off to return from a calling function. Highly organized, small, extremely efficient. A heap is a larger chunk of memory that you can, if you want a lot of memory allocation, you can't do it on the stack because you'll have stack overflow. But if you do want to have millions of integers or something like that, or billions of integers, that's perfectly fine if you allocate it on the heap. The heap is a much larger area. It's a little bit less organized, though. You don't have this on top, on top, on top. You have it can become segmented and fragmented. All right, I need a chunk this big. Okay, well that'll fit right here. Right? I need a chunk this big. Okay, that'll fit right here. Right? I need a chunk just as big. Well, you don't have that chunk right here in the middle, so I'll go ahead and give you another chunk over here. It starts to become fragmented, and some chunks might be wasted. Eventually, it's all cleaned up when your program is done. But that's the basic idea, right? It's kind of similar to this. There's some organization, but there's also some gaps, some fragmentation, and unless you write your own malloc implementation, you really have no control on where it comes from. That's the operating system's responsibility, right? So let's define an in-memory heap, a data structure heap, right? A definition. A heap is a data structure, is a binary tree such that it with the following properties, with the following properties. Right? 1, it's full. Up until possibly the last level, which would be full to the left. And I'll draw you a picture of what this means in a second here. 2, for every key, for every node U, U's key is less than both its children. Or if it only has one child or no children, then by definition it's less. Okay. So what does it mean to be full and except for possibly the last level? It means that it looks kind of like this. Right? It's a full binary tree, except for the last level, and this last level here is full to the left. Right? meaning that there are no gaps in here. All right? All of the nodes are present. All of the children are present in levels from the root down to the second to last level. And in the second to last level, they're all shoved to the left. Right? This is the fullness property. Right? For every node u, u's key is less than both of its children. So we have a situation like this. 10, let's say 20, and 30. Right? Just as a really quick example. Is that a binary search tree? No. Why? Everything over here has to be less. Everything over here has to be greater. Right? And that is greater. But u's key has to be less than both of its children. Right? And this is the heap property. Right? Let me go ahead and give you an example. Right? I'll go ahead and start with 10, 20, 30, let's say 50, 40, 25, 35, I mean. 70, there we go. And then I'll put one over here, 60, let's say. And then put one right here, 65. There's a heap. Is this a heap? Something I haven't used yet, 55. There we go. Is this a heap? It's full at this level, and this level. All of the children are there. And at the last level, it needs to be full and to the left. Is this full and to the left? I've got a gap right here. Right? I've got a gap on the left child of 40. So let's fill in that gap to ensure the fullness property. What could I put there? Could I put 5? Nope. Why not? It has to be greater than its parent. Does it have to have any relationship to its sibling over here? To a left child versus right child? No. It can be less, it can be greater, it can be whatever. The real relationship here is with its parent. So what are my restrictions? If my parent is 40, what could I put in here? Anything larger than 40. I've already used 45. No, I have not, so I'll go ahead and put that in, 45. Right? And now that's a heap. Okay? So let's make some observations about this. Right? So one observation is the fullness property. Fullness property. What does it guarantee? Right? Remember all the way back to Tuesday last week. Why are we looking at binary trees to begin with? If they're full like this, then what kind of guarantee do we have on the depth? It's going to be what? Order log n. Right? So this fullness property seems really, really good because it kind of guarantees what we could not guarantee with regular old binary search trees. Right? What other observation can you glean from this example? What's at the root? What's at the top? The minimum element. The min element is always at the root. Okay? We're going to exploit both of these properties to do those two operations that I was mentioning. We're going to be able to insert elements into a heap such that, one, the heap and fullness properties are preserved. Can't go breaking your heap, right? If you insert something arbitrarily and it's no longer a heap, you need to fix it. In fact, that's what the algorithm is called, is fix heap or heapify. Sometimes it's called. Oh, and then two, with a guarantee that the insertion will be order D, which, because of the fullness property, guarantees that this is going to be order log n. All right? And then we're going to be able to retrieve and remove the minimum element from the heap, such that, again, the heap and fullness properties are preserved. And 2, it'll be order D, which again, because of the fullness property, is guaranteed to be order log n. Right? Those are going to be our 2 goals for next time. Just looking ahead here, what if I got the minimum and I took it off? Right? What kind of a strategy could I take? Again, I kind of hinted at it with the binary search trees. What if I started to promote its children? Right? Which child should you promote to preserve the heap property? Or to preserve that this would have to be less than both of its children. So could I promote 30? No, because that heap property would be violated with 20. So I could promote the minimum, right? Well, that leaves a gap over here. So which one of those could I put up? 40, right? Now I need to put up the minimum, 45. Uh-oh. What happens if I take that strategy there? I will end up having a gap here, and I will no longer have that fullness property, right? I won't have that heap property anymore. So for next time, think about, well, okay, that's not going to work. What else could work? How do I do both of these things? How do I keep the full heap property? How do I keep the fullness property? And how do I guarantee that it's going to be order log n? Right? We'll go through that, both of these, write some pseudocode, and then we'll look at some applications of heaps next time. Right?